Hello. Can anyone reply? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay. So let's begin our discussion. We are on chapter number 2, which is the circuit partitioning. So last few lectures you have seen the which kinds of algorithms possible in general for physical design. Then we enter into the very first step of the design, that is partitioning, where entire complex systems where we have to divide into number of small sub modules. The output of partitioning is the modules as well as interconnection informations between the modules. Major objective function for partitioning, we have to reduce the number of wires between modules. So ultimately we try to improve the speed of our system. So in that sense, we have seen the constructive as well as iterative. Constructive was in 3 category. Iterative started with the first category was min cut, where very first algorithm we have seen that it is called the Kernighan-Lille algorithm, in short KL algorithm. So we have seen 2 problems, examples, graph is given or logic diagram is given. Based on that, we can apply the KL algorithm steps and you can find out the modules and interconnection between the modules. So last problem was, let us quickly see what was the last problem. Anyone try except 2 students? I got the mail from 2 students. Anyone else try for this example?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Sir, hello. Am I audible, sir?
Yes, we are audible.
Sir, I have tried example number 2. In the step number 4, I am having a question.
Yes.
So in step number 3, I have find out the gain, and in step number 4, I have taken one of the maximum gain. Actually, in this particular example, G35 is equal to 3 and G46 is equal to 3.
Hmm?
So if I am taking any of the possibility G35 or G36 for the step number 4,
Huh?
if I am interchanging the node position,
Hmm?
then I have to find the D6 dash. Suppose if I am taking one of the possibility, let us take suppose G35.
Hmm?
So I have to update the node values for 6, 7, 8, 4, 1, and 2.
Hmm?
So regarding updating these values, if I'm consider the node number 6, so
Yes.
node number 6 is associated with, it is connected with 5 node number and 3 node number.
Hmm?
So if I want to write down the equation for D6 dash, then what will be the equation? D6 dash is equal to D6 plus we have to go for the after swapping connection minus before swapping connection. That was the equation.
Yes.
So I'm little bit of confused in D6 dash equation
Okay,
because
well,
both nodes are connected 3 and 5.
yes, yes. I will come to your question. So this is the problem in hand. Initial partition was given 1, 2, 3, 4, 5, 6, 7, 8. Total cut set was 9 initially. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Total 9 cut sets are the initial cut sets. And you have to apply the Kernighan-Lille algorithms to find out the answer. So anyone having the gain equation, first gain value?
Yes, sir.
What is that?
Value or values gain G15, G16, G17.
First,
The G15 equal to 0.
0.
no. Anyone else? Maximum gain value.
So 3.
3.
Yeah, 3. 3
3,
is
3.
correct.
3,
3 is
sir.
correct. 3 is correct. And for that, our choice is 3 and 5. There are two same gains, 3 available two times. So let's we select 3 comma 5 for the interchange. Okay. So if you interchange this,
Sir, 4, 6 is also there, no?
yes, yes. So if, as I said, if two are same, you select anyone. So here I
Okay.
select 3 comma 5.
Yes, sir.
Okay, where G1 is my maximum value plus 3. So if I resketch this diagram, see actually this computer will handle only this calculation. G1, D1, whatever. Computer will not understand this graph. Okay. So what we have to do, let us sketch this graph again. If we interchange 3 and 5, can anyone tell me how many cuts set?
Sir, 6.
Yes, 6 is correct. This is my new partition. So 9 becomes 6. Okay. This is cut set. You can resketch, or you can do the partition like this: 1, 2, 5, 4 in one group, 1, 2, 5 and 4 in one group, and then remaining are in other group. You will get cut set 6. Okay. Now can anyone tell me what is the value of gain G2?
Sir, G2 is 5.
Yes, G2 is 5, absolutely correct, where 4 comma 6 is the selection. 4 comma 6 is our selection. So if I apply this on this partitioning, 4 and 6 I have to interchange. Can anyone tell me how many cuts set?
So 1.
Yes, 1. I am listening only one sound. Maybe my problem here, or others are also giving the answer. So cut set is become 1. Okay. What is G3?
Sir, G3 is minus 6.
Minus 6.
6.
Minus 6 is correct. If you are getting other answer, please check. 1 comma 7 is the selection. 1 comma 7. So if I apply this on this partitioning, let's say A triple dash, 1 and 7 I have to interchange. B triple dash 7 becomes 1. How many cuts, sir?
So 7.
Cut set is 7. Yes, correct. Cut set is 7. Why it is large number? Because gain is negative. That's why. While here the number is small because gain was positive. Now let us see G4.
Sir, minus 2.
Minus 2.
G4 is minus 2. Yes, correct. You are correct. So G4 is minus 2. My partitioning A dash. Oh, which node? 2 and 8. Yes. This I have to interchange. This I have to change. 2 and 8. it becomes original. 7, 8, 5, 6 and 1, 2, 3, 4. Because it is swapping. Whatever on left side becomes right side, whatever on right side it becomes left side. Pair of interchange. And how many cut set?
Minus sign.
9.
9,
9, 9,
because it is
9, 9.
original. It is original. Now here something interesting we are going to see. Which you select? Which gain you select?
Positive gain.
So student have misunderstanding or some in the hurry they are doing the mistake. Most of the chance mistakes occur here. Once they are doing this calculation very fine, but selection is very important. That's why I keep this point separate for today discussion with this example. This is applicable for previous example as well. So if you select as you have to select the maximum gain is 5. You can see it is G2 equal to 5. And Sivan, one of the student in your batch, did this and select the 5 as a maximum gain. Okay. Out of this, all other numbers 3, -6, and 7, like that. So in this case, G2 you can say is a maximum value, is a 5. So you have to interchange 4 and 6. So with this partition, with this initial partition, if you change 4 and 6, what is the cut set?
6.
Yes, remaining student can also verify 6 is correct or not. 4 and 6 I have to interchange. One, 2, 3, 6, and remaining is 5, 4, 7, 8. Something like this. Okay. So total cut set is become 6. Any doubt up till now? This is same as what we did in the first example also. And based on that, you find the cut set here, and the maximum gain of G2 is 5. So if you select 4 and 6 as an interchange, okay, you will get this cut set as a 6. But if you see the diagram, initial diagram, our expectation is this one. 1, 2, 5, 6 in one group, and 3, 7, 4, 8 in other group. Because 6 is again too large number as for the formula. So our expectation is this one. Only one cut set, because it is not a very complex circuit, it is small circuit. So by passing the example with one pass, definitely you get some best answer, which is cut set number 1. This is also true for previous example. If you recall, here there are 2 nodes. There is again 3 nodes and 1 nodes here. Try to recall that example number 1. Initial partition was given like this, but if you apply one pass to that algorithm, we got new result, which is only one cut set, this group and this group. Yes or no? Yes or no?
Yes, sir.
Yes,
Yes.
sir.
So
Yes, sir.
similar way, we are expecting that if you pass this algorithm with one pass, at least we get some minimum number of cut sets. So do not stop here. You have to little bit apply the logic to get this answer, which is applicable for any examples. So we have to take the cumulative summation of each and every gain value, and then we have to see where it becomes maximum. I repeat, we have to take the cumulative summation of each and every value of the gain, and we have to see where it becomes maximum. So first gain value, we found that it was what value it was? 3. Okay. Second gain value is 3 plus 5, which is 8. Third gain value, is it visible on your screen? Because I am to bottom, I am writing. Yes or no? It is visible?
Yes,
Yes,
sir.
sir.
Okay. 3 plus 5, 8 minus 6 minus 2 or plus 2. Okay. And the fourth G4, which is the addition of all 3 plus 5 minus 6, and what was the last? Minus 2. So answer becomes 0. This is for cross check. But you have to stop where your addition becomes the maximum. So if you swap this, if you see this one, okay, so you are interchanging what? You are interchanging which nodes? 3 and 5, okay, with this given initial partitioning, 3 and 5. So if you interchange 3 and 5, you have 5 here and your 3 here. Then you move for the next. Again, you have to interchange 4 and 6 with G2. Maximum value is 8. So 4 and 8 you can also interchange. Is it fine? 4 and 6, sorry. Let me correct. Not 8, 6. So 1, 2, 5, 8, 1, 2, 5, 6 in one group and 3, 7, 4, 8 in other group. 3, 7, 4, 8 and 1, 2, 5, 6. You have to take the cumulative additions and you have to stop where gain becomes maximum. So first pass, first gain value 3. Once you have 3 plus 5, it is 8. Once 8 becomes maximum, then there is no maximum value, plus 2 and 0. So you have to do the swapping up to this. First is 3 and 5, and also second 4 and 6. Not only 4 and 6. If you do only 4 and 6, your cut set is 7. Your cut set was 6, yes, this one. But take the cumulative additions of all the gains. Let's say we talk about this previous example. In the previous example, we got directly first is 2, second is minus 3, and third, can anyone recall me? Third was what? 1. And if you do the addition straightforward is 0, but let's say G1 is 2, then G1 plus G2 is minus 1, then G1 plus G2 plus G3, that becomes 0. So where you stop? You stop here. That is for 1 and 4. So in starting you get this answer. If you interchange 1 and 4, you get only one cursor. But the example like this, where circuit is little bit complex, where 1, 2, 3, 4, 5, 6, 7, 8 number of gates are there. Even it is still applicable. So you can take the cumulative addition of the gain and stop where gain is maximum. So Sivan did this up to 6. We got the 6 cut set by this logic, finding the maximum. But this cumulative addition you have to also apply. Then and then you will get this minimum cut here.
Yes, sir.
I hope I made clear to you, all of you.
Yes, sir.
Yes, sir.
Yes, sir.
Let me share you the answer of Sivan. Is it visible, this screen?
Yes, sir.
So this is one of the student of your batch did this exercise 3 and 5. I hope you all of you also done. This is 3 and 5 swapping. Parthiv, you can find your answer here. And then -6, 1 and 7 is swapping. And then total gain is 0. He selected this 5. But one additional steps you have to apply. You have to do the cumulative addition of all the gain and see where gain is maximum, where it becomes maximum. So he got the answer of 6, but still the 6 is large number from 9. So take cumulative addition. That only one additional step you have to add.
Sir, can you share the PDF?
Yes, definitely. I will share with all of you. So you can check your mistake. But this is
Sir, so we have to stop where gain is maximum.
by doing the cumulative addition.
Okay, sir.
Is it fine?
Yes, sir.
So shall we move ahead or you want to solve other examples? Is it fine? Okay. In exam, if I'm asked any circuit, can you do that? Or still you want to do the practice? What is your choice? All 19 students.
The practice.
You want to solve here at presence or at your home? What is your choice?
Sir, to give us questions, we will solve at home.
Huh? Yes?
Sir, at home.
At home,
Okay.
sir.
So I'm giving your homework, which may be in your exam. I don't know. Try for this diagram. And you have to mail me the answers so I can see that what are the mistakes. I can reply you also. This is also we have seen. Answer is very well known to you. 1, 2, 3, 4, 5, 6.
Sir, your screen is not visible.
Oh yeah, let me share the screen. Now,
Yes, sir.
so there are 8 gates. Initial partitioning is also given. 4 cut set initial. So apply these all steps at your home and see what answer it is there. Without any algorithm, can anyone give the answer? How many cut set after first pass?
So 1, 2, 5, 7, and 3, 6, 4, 8.
1, 2, 5, 7, and 6, 4, 3, 8 means 2 cut set.
Yes, sir.
Yes, 2 cut set is correct.
1, 5, 7,
Whenever,
8.
yeah, other possibilities also there. 1, 2, 5, 7, 8. Sorry, 1, 2, 5, 7.
1, 5, 7, 8.
1, 5, 7, 8. Yes, correct. 1, 5, 7, 8 and 2, 3, 4, 6. That is also possible. 2 cut set. So if you apply all the steps, you are expecting that you have 2 cut set. This is one possibility. Other possibility depends if two gains are same and some students select some other pair, some students select some other pair, but still your answer should be 2 cut set after one pass. In which situations you have to apply second pass, third pass, fourth pass? Which situation? Hello, am I audible?
Yes, sir.
So in which
Yes.
situation you have to apply second pass also, third pass also? This is first pass only. Just we have seen this example, previous example, where 4 gains are there. One value it was 3, second value is 5, minus 6, minus 2. So we found that here we got how many cut sets? 6 cut set we got, 1 cut set we got, and then 7 we got, 7 or 6 I don't know. Then we got some 9 again. But in reality this is not a number. This is good for small circuit. But if your circuit is very large, instead of this one your answer may be 50, 60 also. Okay. So in that case, you have to apply second pass by selecting this pair as a initial partitioning, and whether you have to check that whether this number is reduced or not. So if your circuit is complex, millions of gates are there, definitely it will not work. It will not give the best answer just by one pass. It will give answer by 2 pass, 3 pass, 4 pass like that. And then you can see that it will be minimize the number of cut set between modules. So that is the use of first pass, second pass like that. Circuit is complex, definitely you have to go for next pass also. It is clear?
Yes, sir.
Okay, so let us discuss some disadvantages of this algorithm, and then we'll see. If any doubt at any time you can ask.
सर आपने कहा था पॉजिटिव गेन के लिए ही, आगे वाला प्रोसीजर करना एफिशिएंट होगा, तो हम नेगेटिव गेन के लिए क्यों कैलकुलेट कर रहे थे?
Because we have to complete the procedure for each and every pair of nodes. Not for just one we get positive we stop. We have to see there are 4 nodes here and 4 nodes are here. All 4 we have to swap. This means all 4 here and this all 4 here after one pass. You have to check all gain values. So in some cases you will have positive number also, in some cases you have negative number also. And then you have to decide where it becomes maximum like this. That only 2 times, there are 2 nodes or 2 pairs you have to swap. That is the logic.
लास्ट एग्जांपल में समझ में आ रहा था ना कि मिनिमम स्वैपिंग, मिनिमम नेट लिस्ट क्या 1 है फर्स्ट स्टेप में, तो आगे वाला प्रोसीजर क्यों रिपीट किया हमने?
First example.
नहीं सेकंड वाला,
Second one.
3-5 का स्वैपिंग और 4-6 का स्वैपिंग.
So if I do only, if you see here gain was 5, and if I select only this swapping of 4 and 6, it will result into 6 cut set, which is large number. So cumulative additions you have to do. You have to source 3, the starting point, gain 1, that is 3. Second gain is 3 plus 5, which is my 8. So I have to do swapping of 2 pairs, 3 5 also and 4 6 also. That result into only 1 cut set instead of 6.
ओके सर, और 1 कट सेट आंसर आने के बाद रुक सकते हैं?
If your circuit is like just 8 nodes, 8 gates are there, 10 gates are there, definitely you get best answer, cut set, let's say 1. Here in this case it is 2. 1 is not possible if you see. Anyhow, anyway, if you cut, 1 is not there. So let's say here cut set is best answer is 2. So one pass give you this result. If circuit is too complex, your answer is 50, you have to go for the next pass. Maybe it gives 40 like this. So this initial act as a your, this swapping act as your initial partition. So in your computer, in your software, multiple pass are running, not just one pass, because circuit is very complex in digital design. So here you are getting minimum number because circuit is very small. Here in this case too, previous two example we got one cut set. First example and second example. While here in this homework example, your cut set answer should be 2, because one is anyhow not possible if you apply any cut balance partition. So you have to satisfy with this 2. Is it fine?
सर मतलब नेगेटिव गेन के लिए आगे वाला प्रोसीजर करने की जरूरत नहीं है.
No, because your if you have a negative gain, we have seen the cut set is even larger as compared to previous one. So that's why if you do the cumulative addition 3 plus 5, you are stopped here where your gain becomes maximum 8. So you have to do the swapping of 2 pairs 3 5 4 6.
ओके सर.
Okay, so let us discuss the disadvantages of this algorithm, Kernighan-Lin algorithm. This Kernighan-Lin algorithm is applicable to reduce the number of edges. So this is one node, this is one node. If edge is available like this, you can reduce this number of edges by using this Kernighan-Lin algorithm. This algorithm is not applicable if the case like this. Single net which is connected with more than 2 nodes. Here it is 3 nodes. Single net which is connected with more than 2 nodes. If it is available like this, single net which is connected with only 2 nodes we call as a edge. But if it is connected with so many number of nodes, more than 2, then we call as a net. So if this is the situation, this Kernighan-Lin algorithms is not applicable to reduce the number of nets. It is applicable to reduce the number of edges. This is called multi-net. In any graph, if any edge or any net is connected with more than 2 nodes, that edges or that graph you call as a hypergraph. Kernighan-Lin algorithms only reduce the number of edges, while for hypergraph where single net is connected with too many number of nodes, more than 2, the multi-net hypergraph. So in that situation, this algorithm will not work.
Sir, which type of circuit is represented by hypergraph?
Hypergraph means can I sketch the diagram like that?
Yes, sir.
Yes. So this is the diagram. Let's say 1, 2, 3 node. Fourth node is also there. ABCD. Let's say. Something like this. And here we are adding one more node. This is multi-net. This is not handled by the Kernighan-Lin algorithms. Because Kernighan-Lin algorithms only take the pair of nodes swapping. So only minimize the edges, which is cut between two. But this is the situation, multi-net situation is there. A single net is connected with 100, 200 nodes, for example. That case, that is called hypergraph. In that case, it's not able to handle by this Kernighan-Lin algorithms. So that is one problem in this.
Sir, like which Boolean expression circuit can be represented by hypergraph? Like in previous example, we have number of NAND gates, so we represent it in graph. So which type of circuit? Yeah.
So yeah, I'm saying any digital circuits definitely we are representing with the graph. But interconnections are very important in the physical design. We are not going to touch what is available inside this NAND gate. So we represent with vertices or nodes. These all kinds of nodes. Maybe it is any gate XYZ. But interconnection between this gate is very important. If interconnection is like this, only output of first NAND gate is connected with input of second NAND gate, you have only one wire like this. But the circuit like this, your second gate is also there. This is multi-net. Okay, this is the situation. And your KL algorithm is
Okay, sir.
not able to work. This is hyper. If you sketch the graph of this diagram, it is hypergraph with multi-net. Because this net, this gate is connected with this also as well as this also. So in that situation, you cannot do the swapping of single node with two nodes like this. You can select pair only in the case of Kernighan-Lin algorithms. So in that situation, your Kernighan-Lin algorithm is not work. KL algorithm will not work for multi-net. Multi-net, it means single net which is connected with more than two nodes. So that is one problem. Suppose second problem we are discussing. Let's say I'm giving the size of each and every gates or each and every nodes. Let's say 1, 2, 3, and size of here is also 1, 2, 3 or some 4, 5, 6. Let's say size of each node. And if you do the swapping, does it remain the same size in this partitioning and this partitioning? You do the interchange. Size is what we assumed previously in KL algorithm. We assume that size of each node or gate is same, equal size. So if you do the swapping of equal size, let's say this is also 1, 1, 1. These all 6 are 1, 1, 1 instead of different number. So total size of this partitioning is 3. Total size of this partitioning is 3. And if you now do the swapping, okay, so this 3 remain here as it is, this 3 remain here as it is. So KL algorithms works only in the situation where size of each and every gates are same. But if the size of each and every gate, some gate is NAND gate, some gates are OR gate, size is different. And then if you do the swapping, this balance criteria is not maintained. So it gives result into the unbalanced output. Partition A, maybe total size is let's say 25, and partition B, total size is only 16. Balance is not maintained between two partitioning. KL algorithm will not work if size of each and every gates are different. Is it fine?
Yes, sir.
Okay. So let's discuss the third and very important disadvantages. Which we call as a runtime complexity. Runtime complexity. this we discuss in chapter number 1. This we discuss in chapter number 1 for each and every algorithm. For each and every algorithms, we have to check the runtime complexity with asymptotic notations O. Inside we have some variable which is our n. So if I have a single node, if I want to calculate the d value, d is called the development. What is the runtime complexity? If I have a single node, okay, if I want to calculate d values, this is the development external cost minus internal cost. What is the runtime complexity?
One.
Okay, so if there are n number of nodes, what is runtime complexity?
N.
Yes, O of n, asymptotic O of n. So if there are n number of nodes, this complexity is there. Now suppose in Cunnington-Lin algorithms, I have to calculate D or gains, everything for other partitioning also, if you recall the steps. So now can you tell me what is the runtime complexity for pair?
Sir, N square.
Yes, exactly, n square. So if you see, if you recall all the steps, we are calculating D value and equal number of G value. Then D dash value equal number of G dash value. Then D double dash value equal number of G double dash value, like that. So ON square, okay, I repeat, if I pick up the single node, okay, this is my node or gate, whatever you can say. And if I want to calculate the external and internal cost, which is difference we call as a development D. So in that case, I require 1 unit of time to do this because it is single node. Let's say 1 second is required to calculate this external cost minus internal cost. There are n number of nodes are there, then runtime complexity is O of n. If I want to do the calculation for 2 nodes, because this Cunnington-Lin algorithms works on swapping. तो यहाँ के जितने नोड है उसकी भी डी वैल्यू चाहिए, यहाँ के जितने नोड्स है उसकी भी डी वैल्यू एंड जी वैल्यू चाहिए. If you recall the steps, so O n square complexity. Is it fine?
Yes, sir.
And one more additional complexity you require, just you have seen today, to find out the maximum gain. Okay, G1 do the cumulative summations and then see the maximum gain of this Cunnington-Lin algorithm. So total complexity O n cube runtime complexity of these algorithms. Third, we add also, because to calculate maximum gain, if you recall, this was the last step. After that, all the D calculation, all the G calculation. For that, we have to also write some loop, okay, to do the cumulative summations and all that, and then check the maximum gain. So this O n cube. So runtime complexity is O n cube. So if I'm saying n equal to 10, just 10 nodes are there, okay, and then it is O10 cube. In reality, it is not 10, 10,000, 20,000, or 10 raised to 10. So you can imagine runtime complexity. These algorithms require long time to give the output. The runtime complexity is O n cube. The third disadvantage. So we have to handle this all the problems of this Cunnington-Lin algorithms, runtime complexity, balance partitioning with the size. It should be able to handle the multi-net hypergraph also. These all limitations we have to overcome by some modification in the algorithm. So we are going to start with the second algorithm, which is used to remove this all the problem of this scale algorithm. Shall we begin? Second iterative algorithm in the partitioning.
Yes,
Or
sir.
if you want to ask any questions, you can ask, no problem. Debussy-Matrici algorithms, in short, it is called FM algorithms. This is the scientist that invented this algorithms. It's called Debussy-Matrici algorithms, like Kernighan algorithms. Now we are looking this FM algorithms, which used to remove all the disadvantages associated with the KL algorithm. So again, here we are going to see some features of this FM algorithm, how this algorithm is different from the KL algorithms, what are the steps, iterations you have to apply in such a way that we are able to achieve the minimum interconnection between modules. So first and foremost, that is the multinet. This algorithm is applicable for multinet. It means the net, okay, which is common for 3 nodes, more than 2 nodes, still you can apply this algorithm as a FM algorithms. Actually, this is more realistic, more practical situation. In your actual digital designs, it is not like that only one gate is connected with one wire. It is definitely this output we are taking with some other input also, like this. So this FM algorithms actually is a practical solution of the partitioning, which gives the reduction in number of nets between modules, while KL algorithms reduce the number of edges. Number of edges is reduced between partitioning. That is the job of KL algorithm. But here, these algorithms work for the nets reduction. Number of nets is reduced between two partitioning. So that we are going to check with this FM algorithm. That is the first features of this algorithm. It will work on nets, while KL algorithms works only on the edges. Here, second feature, all the gates have different size. What is the size in KL algorithm? All gates have
Equal.
equal size, but here you can say NAND gate, NOR gate, any other gate also of different size, and still you can do the partitioning. So all the gates have different size. So this is also more realistic situation. You don't have any digital design where only one gate is used. We have multiple varieties, maybe OR gate, NOR gate, whose size is different. Even NAND to NAND gate size are different, depends on area, power, speed constraint. So this is more realistic. You can take some different size of the gates and you can do the partitioning. So this is the main two features we are going to see for this algorithm. Let me give you one circuit. One, you can indicate circle also, no problem. These are my nodes, or it is also called the cell. And this is the partition. Initial partition is always there because it is a iterative algorithm. So 1, 2, 3 in one case, one side, 4, 5, 6 on other side. Let me give the net name also. M, Q, K, P, and J. Which nets are multi-net? Can anyone tell me?
Q.
M and Q, correct. Okay, so this kind of problem is not possible with solution is not possible with KL algorithms where this situation is there multi-nets are available. This we have to solve only and only with this Fabiosi-Mattesi algorithm, FM algorithms. Okay, let me give you the size of each gate also. S stands for size. Size of each cell, each gate is given. 3, 2, 4, 1, 3, 5. What is total here? 9. This is also 9. So partitioning A size is 9 initially and B size is also 9. Can if you move the cells from here to here or here to here, this size remains same or it is changed? 9, 9. Hello?
So changes.
Yes, definitely it is changed because all the gates have some different size. So if you try to do the interchange of the cells, interchange of the gates, interchange of the node, size is not remain as it is. So there are some in this algorithm, there are some size constraint factor which is called the balance criteria. If you're if you maintain this criteria, it is possible that you can do the changes. Size of A divided by size of A plus size of B, which is 0.5 at present. 9 upon 9 plus 9, okay, 0.5. So if you cross this one or if you are within this limit, you can allow the changes. Because size is a constraint, so some balance criteria is defined, which is size of A upon size of A plus size of B. If you are within this range, no problem to change the nodes, to swap the nodes like that. It is possible. Third and very important third and important feature of this FM algorithms, we are not going to do the swapping of the node. We are just going to move the individual cells, individual gates from this side to this side or from this side to this side. No swapping. So if we pick up, let's say number 1 based on gain calculation and everything, only that cell I have to move from this side to this side. No any other node at that time will swap from B to A. So it is movement of cell. While in the case of KL algorithms, we have to swap the pair 3 and 4, let's say 3 and 5 interchange. But here only one node we are going to swap. Only one node we are going to move from here to here or any other node from B to A. So this algorithms works on individual cell, while previous algorithms between two cells, between two nodes. So these three important features, it's applicable for multi-net. Some balance criteria is given and different size of the gate is there. That's why balance criteria we have to satisfy, and it will work on individual cell. Cell movement you can allow. Yes, yes, you can ask. Hello, your voice is not clear. You are not audible.
Sir, hello.
Yes, can you speak?
Hello.
Yes, you can speak. You are audible now. Tirth,
Sir, sir means in this figure we can swap 1 and 4.
I said that swapping is you have to work on individual cell. So one you can move from here to here, but at the same time another node from another partition will not allow. Only one node you can swap.
Sir, can you give one
So
example?
so suppose you after doing the gain calculation and everything you find that gain of this cell is maximum. So only that cell you can allow to move from A to B. Once you move that again do the gain calculation, let's say you come to know that you can do the movement of these two. So only these two you can move from A to B. Next time again you calculate the gain and you can find out that this 5 has a maximum gain. So only 5 you can move. While previously what we did in KL, we are moving the pair. एक यहाँ पे आएगा तो दूसरा सामने change होगा. Let's say 4 and 1 are interchanged. Here only single individual cell we have to move. That is cell movement, not pair. Am I clear, Tirth?
Yes, sir. Yes, sir.
Okay, good. So we stop here. We'll continue tomorrow with these features with real examples. Meanwhile, if you doubt, you can ask by email, no problem. And try to solve the what example homework I given. I will ask definitely in starting what is your answer. Okay.
Sir,
Yes.
sir, I just want to ask that we have to do them in MATLAB on our own.
No. I will give you some hint. Then you will start. On the Friday, we'll start that second experiment. Okay. So if you are good in programming, you can definitely start. But I will give some hint. Then and then, if possible, you can start.
So,
Yes.
sir, can you explain once that last question with 4 and 1 cell was there? If we can mention that.
So in yes, in KL algorithms, what we are doing, there are, let's say, one partition, second partition. We are doing the swapping of nodes. ये 1 and 4 है, तो हम swap करेंगे 4 यहाँ पे और 1 यहाँ पे. But in case of FM algorithms, suppose 1 यहाँ पे, 4 यहाँ पे, 5, some other numbers are also. We have to move only one node here. And then we have to check how many interconnections are there. Not pair.
Okay.
So we'll meet tomorrow and we'll discuss length with example. Thank you for joining. If you have any doubt, you can mail me and definitely you do that example homework.
Thank you, sir.
Thank you, sir.
Thank you.